Okay, so let's start. So just continue on clock skew, and we're gonna finish this topic. Move on to arithmetic circuits. So we said for clock skew, if there is a delay there, we already saw that it has an effect on our clock period, so it makes our clock period worse, or the minimum clock period longer. So because of this D here, right? Because of the delay, that's what we covered last time. So that's one effect. One effect of clock skew is we have to take into account the delay in the worst case path, and that basically makes our clock has to be slower in order to meet timing with clock skew. So that's generally not a good thing. So that's one effect, and there are a few other effects of clock skew, which we should note. It can cause also hold time and setup time violations. So actually, in this case, I think it's causing a setup time violation, but a clock hold time violation would be very similar. Essentially, if I have the clock here, if there's a delay here of the clock B, right? So when clock A changes, right? Clock A changes. We have T clock to Q later. We have whatever is in A will go to B, right? Whatever in A will pass to B, right? So it goes from here to here, right? And if the clock of B is delayed so that its setup hold window is here instead of exactly where it was for the first flip-flop, right? Then that transition could happen within the setup hold window. So it could either happen within the setup time or the hold time. It really depends on exactly what delay it is, right? So that either case is of course bad, right? We don't want setup time setup or hold time violations, right? Now. So that's so there's one effect clock. So the one we talked about previously is clock. The clock period is we have to take into account D, right? The clock period is going to be longer. You can also say that's sort of like take into account setup time, right? Because the clock period is basically that's what the setup time is taking into account. So that's one effect, and the other effect is that we could say that if the delay here is such so that whatever comes here changes during the setup hold window, right, and violates the hold time, then this would be a hold time violation, right? Again, setup time, let's wrap it into the previous case of making the clock a little bit slower. So clock longer, one effect. The hold time violations, we could get a second effect, and then there's a third effect that could happen, right? Which is we can have functional programs even if hold time or setup time is not an issue. I mean, if there's so let's see what happens here. If we have so S1 going into the flip flop coming out as S2, there's some logic here. And then we call this point S3 and this point S4. So assuming there's no skew, and assuming this is a data like 46, 47, 48, which is for convenience, just increasing so we know which one comes when, then, when there's a clock here in S1, then S2 becomes 46. Okay, S1 going into S2, right? S1 going into S2 after the clock, right? After the clock. And after delay, there's delay here, right? I thought this was S3. No, this is S3. After a little bit of delay, it becomes 46. And then the next clock, whatever is an S1 goes to S2, right? That makes sense, right? A little bit of delay is goes into S3, and since we had 46 here, right before the clock edge, then it now becomes S4, right? So that's just normal operation, right? Whatever is in the before the clock edge, you know, setup time is met, goes to the end, goes to the queue, right? Whatever is in D goes to the queue, and whatever is in D here goes to the queue, right? S3 to S4, S1 to S2. That's all normal. What happens when there's skew, right? So when there's skew, right? When there's skew, if the skew is right, or if you will, wrong, then so clock, whatever's in S1 goes to S2 in the clock, right? Okay, it passes through the logic. Okay, it passes through the logic before the next clock edge, because the clock edge now is delayed on clock B, right? The clock edge is delayed on clock B, and that means that now in S4 I will get whatever was in S1, where I should have gotten 47, right? If you recall the previous correct, sorry, right? I got 46 here, right? I got 46 here, not here, right? Here it was 45, if you will. Okay? So, so that would be a functional issue, right? A functional issue. I didn't have a setup time violation here. I didn't have a hold time violation here, but I did have a functional issue due to 46. It's sort of like a hold. It's not a hold time violation because I'm outside of the hold window, but it's you can call it sort of it's not a hold time violation technically, but the data here changed before the clock, right? When it shouldn't have, right? It changed too fast. It changed too fast because the clock was delayed, right? You with me? I'm not sure. I'm hoping. So because this clock was delayed, this part here changed before the clock, and that caused the wrong value to go into the flip-flop, even though it didn't cause a hold time violation. If it were a little slower, it would have caused a hold time violation, maybe. If the data was a little slower, it would have caused a hold time violation. It might have fallen into the hold time, but it wasn't. So there's three effects. Again, you have to make your clock slower. There could be hold time violations that that cause obviously metastability or wrong value to go into the flip-flop. And the third thing is there could be, you know, not hold time violations and not setup time violations, but still the wrong data would go into the flip-flop. So obviously clock skew is not a good thing, right? So clock skew needs to be avoided, right? That's the bottom line. Now I will comment here. What will happen essentially is that the compiler recognizes this. The good news is the compiler knows this, right? The compiler knows that there's clock skew, right? It has the device modules. It knows that there's clock skew. It will add, essentially what it will do is add a delay here, a delay D, which will sort of match the delay of the skew, right? To make sure, not necessarily the same D, but I'm talking about, it will add delay to match the skew, because remember there's delay here as well, right? So it will make the calculations, you know, worst case, so fastest path, worst case the slowed path and the fastest path, and it will set up a delay so that you know, hold time and setup time will be met if it can. Sometimes it can't, and it'll give you a timing error, but if it can, it'll do that. So what you have to do as a designer is look at those timing reports and make sure that the compiler tells you that it has met timing even with this skew, right? And sometimes it'll tell you that it can't do it. Okay? So in any case, the moral is clock skew needs to be avoided as much as possible. So what can we do to help with clock skew, right? That's the question here. So if we have a custom chip, so an ASIC, then complete control. We can minimize skew as much as we can, given the technology. One way is to just control the routing of the clock. If we are making a custom chip, obviously we can do that, right? So there's a common thing called the H tree, right, where you can see that the path to each flip-flop here from the clock is the same length, right, or basically the same delay, right? So as long as that is controlled to a good tolerance, then we've got very minimal skew and no problem, right? But that's only if we have control over the routing, right? Which would mean that we're making our own chip. So in an FPGA, we wouldn't have this control. So yeah, so you can see if this is like schematically what's going on there, then there is the same amount of delay. In this case, 3 routing sections to each flip-flop, right? So that would be great if we could do it. In an FPGA, we can't really do that. In an FPGA, we're limited to what the FPGA provides to us. And there are 2 fundamental types of clock in an FPGA, right? So one of them is called global clock. And global clock is, it goes to all the flip-flops in the FPGA, right? Just like an ASIC. So very little skew. We're talking about sub-nanosecond skew, like 0.1, 0.2 second skew. So effectively no skew, right? And it goes to all the flip-flops. The only problem is there isn't a lot of them, because those are fixed routings within the chip, right? So there's each of them basically takes up a layer of the chip, essentially, right? So there aren't many of them. And I would say, in the high-end chips, you get a few dozen. In the low-end chip, you get, less than 10, right? So you can't just assign every clock in your system to a global clock. I mean, if you got one clock in your system, that's fantastic. Just put it as a global clock, no skew problems, end of story. If you've got many, many clocks, and I've got designs that's got 200 clocks on them, it's typical for big designs, then you just can't use global clocking for all your clock. Then there's so you have to use them wisely, and I'll talk about what wisely means in a minute. The other type of clock is local clocks. Now, local clocks, what local clocks are is they just go through the routing matrix, right? You have this routing matrix, right, where all the data is routed. You can also route clocks through it, no problem. The only problem with that is, you're going through a bunch of, those routing blocks, right? If you recall the FPGA, maybe I'll put that slide up. Let's put that slide up there. From lecture 1, right? Let's put the slide up from lecture 1. Find that slide. Yeah, I mean, right? We've got right? We go from logic block to logic block through the routing matrix, right? From logic block CLB to CLB through it's called PSM, programmable switch matrix, right? So if we had a flip-flop here and say a flip-flop here and a flip-flop here, we'd go through this routing matrix, right? We'd go like this direction with the data and the clock, right? One path would be the data, one path would be the clock. Okay, that's fine. The only problem is, you're going through routing matrix, you are adding paths to the clock and the data, and the tools have a model of that, a mathematical model of what is the delay through that routing matrix. and there is some tolerance to that model. And every time you add another of these routing blocks to that path, your tolerance gets wider. You're less and less confident in what that delay is, because the actual delay in the device is not exactly what the mathematical modules say, right? So the more of the switch matrix you have to pass through, the less confidence you have in exactly how much delay you have, which means that your clock skew could be significant, right? Especially if we're talking about to a lot of flip-flops over a lot of the device. First of all, so not even talking about the confidence, the skew could be significant, right? If I've got from here to here, if I've got a path with a clock, and from here to here, I've got a path with the same clock, the delay of the clock will be significantly longer from here to here than from here to here, right? Oh, wait a minute. Can you see my cursor? Tell me if you can't see my cursor, right? I have to put a laser pointer there. You see? So from here to here, right? From here to here, the delay will be short if you go through I'm going through just one programmable switch matrix, and from here to here, the delay will be long, right? So it's long clock skew, right? From one flip-flop to another, it's so let's say I've got from here to here I've got a path, and from here to here I've got a path, and from here to here. Maybe I'll draw it. Here, I'll draw it for you. I've got a path from here to here, right? From here to here. Not sure why it's black. It's always red before, but anyway, I've got a path from here to here, right? And I've got a path, say, from here to here, right? The delay of the clock from here to here will be significantly different than the delay of the clock from here to here. And also, if we talk about this diagram where we've got flip-flops which are connected to each other, right? The data could be also, the data path also goes through the switch matrix, right? So if I have a data going from, say, from here to here, which is short, and from here to here back, which is long, right? I've got significantly different data delays, right? And significantly different clock delays going through these flip-flops. So the bottom line is, going through the programmable switch matrix introduces potentially significant skew, and also reduces the confidence that the compiler has in how much exactly skew there is, right? Because again, the mathematical models that it has are not completely exactly what there is in the device, right? So, yeah. So going back to this slide set, so that's what's called local clocks. So local clocks are slower because they have to pass through the switch matrix, and they are prone to clock skew. But the good news is you can have an unlimited number of them, right? Because just like data signals, you can put, well, not unlimited, right? Depends on how many routes you have in the FPGA, but effectively unlimited. You've got hundreds of thousands of potential routes there. So, so what's the strategy? What's the strategy in assigning global clocks and local clocks, and also what is the way to make sure that we don't have skew problems? So first of all, if you try to have as little as clock domains as possible. So if you got just one, that's great. And of course you make it a global clock, right? So no skew, no problem. Now if you've got more than one, first of all, try to use the global clocks. If you've got more than the number of global clocks in the device, then what do you do, right? So yeah, so let's say you've got, you basically have to use this sort of sorry. Let's do this decision matrix more or less, right? Speed So let's do low. So if I have high fan out and high speed, so I need to get a lot of flip-flops, high fan out, and I need to do it fast, then I should use a global clock, right? So the prioritizing which one should use a global clock. If I have low speed, low fan out, right? Low speed, low fan out. I can take a hit on my clock period, right? I don't have a lot of flip-flops that the compiler needs to connect this clock to, so the uncertainty will not be too bad. And batch them together, right? The compiler, if there's not a lot of flip-flops, will probably put them together, so it will be, it can use a local clock, right? The hit we take is not so bad if it's got a low speed and low fan out, right? So those are the really, really clear cases, right? The rest of them are really judgment calls, right? The rest of them are judgment calls. So, you know, for high speed, for example, for high speed but low fan out, what do you use? You know, you don't have a lot of margin because it's high speed, right? So any skew that eats up into your margin over clock is bad. However, if there's like just 10 flip-flops doing it, maybe the local clocks can handle it, right? And maybe you're better off preserving your global clocks for something else, like maybe high fan out and low speed and low speed. A high fan out, if I've got 1,000 flip-flops, right? Even if they're low speed, maybe it's worthwhile to put a global clock there because you know, if there's 1,000 flip-flops, statistically speaking, one of them will have problems if I put them through a local network and not through the global clock, right? So this is really a judgment call, right? In most cases. Now, the tools these days assign them automatically, the global clocks, usually by default. So they will basically make the decision for you. I mean, they basically do this. Obviously, they do this first. Assign. I mean, they don't really assign global clocks and local clocks. They just assign the global clocks. Everything that's not global becomes local, right? Everything that is not assigned a global routing network becomes a local clock. So they assign the global clock based on what's my high speed signals, what's my high fan out signals, and if there's anything left over, it'll use some algorithm to prioritize the rest of them. And after everything is done, it gives you a report telling you, you know, if timing was met, including, and it takes into account skew for everyone, including the global clocks, but that's small, but including the local clocks, where the skew can be pretty big. And then you have to look at those reports and see if your design met timing, which includes skew analysis that the compiler gives to you. Okay, so at that point, you should look at, you know, if you see any problems, you should look at the report and see which clocks were assigned to be global and make sure the compiler made a good choice. And if it didn't, you need to assign manually the clocks to be, some clocks to be global, which you think would give better results, right? And there are primitives to do it. So I think it's called, I think it's just called global in Altera. In Xilinx, it's called clock G. Clock G. For example, this is Xilinx. So it's just a, you know, a Verilog model which would give, you know, the clock and the output would be the global clock, and you would use the output. Right? Just the Verilog module, right? And in Altera, it's called global, I believe, just global. So this happens quite a lot. Quite a lot. The compiler will not do a perfect job, and you would need to specifically set clocks to be global. Any questions? Global clocks, local clocks? It's very important. That's one of the most common issues you'll encounter in compiling big designs. In any case. Now, okay, what do you do if your compiler reports that I've tried to fight, but the clock skew is just too bad. I can't handle it. You know, I'm getting timing errors, and usually will be the local clocks, right? And they're because of skew, right? They're going to be timing errors because, say, for example, your delay is too long, right? In between two flip-flops, right? In that case, you can either reduce your clock rate or maybe do some pipelining, right? That's one thing. But if the compiler says I can't meet timing because of skew, right? You've got too much skew in this clock, and I can't compensate in the data to meet both setup and hold time. Then what can you do, right? So again, one thing is maybe see if there's a global clock available. Use a global clock. But let's say there isn't, right? There isn't a global clock. Now what can you do? Well, one way to do it is to use what's called domino logic. So to have like not two clocks clocked by the same clock, but every second clock clocked by the inverse of the clock. So every, say, odd register here, if we keep naming them by reg 1, reg 2, reg 3, reg 4, every odd one will be clocked by the clock, and every even one will be clocked by the inverse, right? And what this does is it makes sure that, you know, when this clock happens, you know, data goes clock to queue and then passes through the logic. Nothing happens in register 2 for half a period, right? It's got half a period for everything to settle down, and and only then it's being clocked, right? So you don't have this race condition where the source and destination flip-flop are passing data from D to Q at the same time. That's what was causing all the problems, right? That they were passing at the same time, but not really, because one clock was a little bit delayed, right? With me? Yeah. Now they're passing. One is passing data. The other one is completely quiet. And after half a period, the other one is active, but the one that was active before is not active, right? So that ensures you're more immune to skew, because you've got this whole half period where you don't really care what happens as long as it settles before that half period comes on. There can be a little bit of skew here. It doesn't matter. It doesn't really matter as long as the skew is not relevant, is not significant compared to the clock, right? So if I got this clock here, right? So this is clock, and the inverse clock is this, right? The inverse clock. So this is clock, and this is not, right? So here we've got, you know, red 1 changing, okay, and here we've got red 2 changing, right? Red 2 changing. So red 1 and red 3, right? Red 3 we should say, and this is red 2, red 4, etc. Right? All the right? Etc. So here the data in the queue of red 1 change. It's got all this half period to propagate before I even look at it at reg 2, right? And if there is a little bit of skew here, you know, if this is, you know, like this, okay, but still I've got almost half a period, right? See the idea here? Yeah? But, of course, nothing's free, right? Okay, first of all, does this look familiar to something, similar to something we've already talked about? Pipelining, right? It's just very similar, except that instead of having the same clock for all the registers, we use half a clock, not half a clock, but the inverse clock for alternating registers, right? So it's very similar to pipelining, but in pipelining we had the whole clock period, right? We had the whole original clock period. Here we've got between registers we've got just half the clock period, right? Because we've got half a clock. So it's great in terms of skew, right? Because it gives us a lot of immunity in terms of skew, but in terms of how much logic we can put between them stages, it's half the delay that we could have put if we didn't have to invert the clock, right? So there is, if we use this logic, we have to, of course, be clear on the fact that we've only got half a period between the registers for the logic to finish toggling, right? You all with me? Yeah? So nothing is free, right? Yeah. So one other thing, okay, so what if, what if you already, so let's go one step further. What if your circuit already uses the clock and the inverse clock, right? So here you can see, what if, this is my topology. I can't add in this inversion of the clock because it's already what I am using, and if you look at Reg 4, for example, here, and Reg 3, Reg 4 and Reg 3, so they are getting their output from Reg 2, right? But Reg 4 is getting it at the rising edge of the clock, and Reg 3 is getting it at the falling edge of the clock relative to Reg 2, right? You see that? Yeah? So if I put a knot here, if I said, okay, I'm going to put a knot here, okay, and make sure that Reg 4 does not change at the same time as Reg 2, right? This would change my design functionally, right? Because now Reg 3 and Reg 4 are changing at the same time. Maybe that's not something I wanted. Maybe I wanted them to change at different times, Reg 3 and Reg 4, right? See what I'm saying? With me? Yeah? So, okay, so I can't just, obviously I can't just invert without taking into account functional considerations. So what if I've got this sort of topology? What do I do? I can tell from experience, this is exactly, so this is like this from personal experience. I had this topology, right? I had something that had exactly this topology. It used the local clock because I ran out of global clocks, and the compiler told me I'm meeting skew. He told me your design meets timing, right? So I'm like, great, design meets timing. I'm done. Only problem is it didn't work, right? The design didn't work. So I looked at my code. The code looked fine. I looked at it again. Still looked fine. So I'm telling myself, what's going on? Why is the compiler telling me everything is fine? My design looks fine. It's still not working. Well, you have to trust the tools until you don't trust them, right? At some point, the tools may tell you everything is fine, and it's not fine. Why? Because their models are only good up to a point. If you have especially when we're talking about local clocks, which go through the switch matrix, like I said, the confidence becomes lower and lower as there are more destination flip-flops, and as it goes through more switch matrices. So, simply put, the compiler may tell you that everything is fine, and it's not fine. And you have to be smart enough to recognize this situation. And this will occur when you see that you've got a local clock with a lot of destinations, and when the skew is maybe you meet timing but not by a lot. You might suspect, okay, maybe the compiler is not telling me exactly what's going on. So that's what I suspected. So what I did is the following. I made a module called hold gen, which like the thinking was generate hold time, right? And what this module does is the following. It takes the clock. You can see what it does here. It takes the clock here, which goes to Reg 2. So the clock that goes to Reg 2, I am delaying it by 2 flip-flops, right? Why 2 flip-flops, by the way? Not 1. Why 2? Talked about this in previous classes. Come on. People should know this. Why not 1 flip-flop? Sorry, metastability, right? Exactly, because if I'm sampling them with a faster clock, and then which just assume asynchronous to this clock, and I can't just sample it with one flip-flop because it could be metastable here, and as we know, metastability, especially on a clock input, is not good, right? So I'm putting it through 2 flip-flops. So what does that accomplish? It delays it by between 1 and 2 clock periods, right? So it could be like a little bit more than 1 because it has to go clock to Q. If it arrives just before the clock, right? Then it will be clock to Q, and then another clock period and of fast clock, and another clock to Q. That would be a little bit more than 1, and it could be a little bit more than 2, right? If I arrive at the wrong place here and there's a timing error or set up hold time violation here, and so it delays a clock, right? We talked about that. There's a 1 clock variability there in there, but so between a little more than 1, a little more than 2 fast clock periods, I get a clock in Reg 5. So whatever skew, so basically I'm delaying the clock here. So Reg 5 will only change 2 clock periods, fast clock periods, after the rising edge of the clock here, right? Which means that assuming that I've got the same clock here, right? I've got the same clock, then this register and this register will have already settled by this time, right? So let's say this delay here is 10 nanoseconds per clock period. So let's say I got between 10 and 20 nanoseconds. That's way more than any skew I would have here. I would have like maybe a nanosecond or 2 skew. So which means that this register will already have put in whatever it had at its input, and then this changes, which would change whatever comes here, right? People follow me, or did I lose everyone? Did I lose someone? Right? The point. What was the problem here? The problem here was these two, Reg 2 and Reg 4, changed at the same time, right? With the same clock edge, but there was skew going to Reg 4, which caused us problems in this path, right? Just like we saw before, when 2 flip-flops have the same clock but with skew, right? And I couldn't just do what I did with Reg 3, which is, have put a knot here, because the knot is already part of the architecture. If I put a knot here, it would change the functionality of Reg 3 versus Reg 4. They would both change at the same clock edge, where I wanted them to change in different clock edge. So I can't use the solution for Reg 4. What I can do for Reg 4 is delay the data going into it in order to give it time, in order to give the clock time to get here and change Reg 4, and only then, after a little bit more time, whatever's in the input of Reg 4 will change, right? So I'm fighting the skew by artificially delaying the data path, right? So again, the compiler should have done this for me. The compiler should have delayed the data path for me, right? But if it can't do it, if it reports that it can't do it, or even if it reports that it can do it, but it still doesn't work, and you suspect that the reporting is wrong, then this could be a solution. I'm artificially delaying the data path to wait for the skew to already pass, for the clock to happen at Reg 4, and then only allow the data to change. Following me? Right? And here, I mean, I do have to pay attention to the path between Reg 2 and Reg 4. I can't ignore it completely, but it's much more immune to skew, right? So as long as I don't eat up, with this delay, I don't eat up too much of the period, right? I've got half a period between Reg 2 and Reg 4, right? Sorry, Reg 2 and Reg 3, half a period. So as long as these 2 fast clock periods don't eat up too much of my clock, then it doesn't matter, right? And I should mention, clock skew problems. Clock skew problems are if I have a clock here, so important observation is if I have so got edge 1, edge 2. I've got some delay here, E, right? And whatever. Okay. If there's so let's say there's like a 2 nanosecond delay here, right? And here I've got 1 nanosecond, and I've got a 1 nanosecond hold setup time, right? Just as an example, a terrible example, right? So ignoring all other delays, right? So I've got once I got a clock change here, right? Ignore clock to Q, say it's clock to Q, T clock to Q is 0, just say. Or you know what, let's put 0.9 nanosecond, and clock to Q would be 0.1, right? So once a clock happens here, I've got 0.1 clock to Q, 1 nanosecond delay of the logic, and 0.9 set of hold time. So I've got 2 nanoseconds here to, this has to be 1 nanosecond or 0.9 nanoseconds before the setup time. I can have a clock period of 2 nanoseconds, right? The total clock period, right? T clock to Q plus delay plus 2. Here I've got a 2 nanosecond delay, right? 2 nanosecond delay, right? Or actually, hold on. I just want to create a setup time violation like all the time. So if I have, let's do this. I just want to create just a situation where I have, let's do this, 0.9, right? So ignore the setup. I've got a 1 nanosecond clock, 1 nanosecond delay. So I've got a 0.1 plus 0.9. This arrives here 1 nanosecond later, and the clock also arrives 1 nanosecond later, right? Yeah? With me? So essentially the clock arrives exactly the same time as the data, right? And that's not good. I need, let's make it 0.5 nanoseconds. I need 0.5 nanoseconds setup time before the clock arrives. So I'm definitely always causing a setup violation here, right? Every time I got a clock, it takes it 1 nanosecond to get here. The data takes the clock to get 1 nanosecond to get here, and that's not good because I needed the data to be stable 0.5 nanoseconds before the clock, right? With me? Yes? I needed the clock to arrive at least 0.5 nanoseconds before, after the data, and here they arrive essentially at the same time, okay? Now, nowhere in this diagram did the clock frequency play any role. If this clock frequency was 50 megahertz, if this clock frequency was once a day, it doesn't matter. I would have gotten a setup violation every time I have a clock, right? With me? So, clock skew is one of those things where they can cause you problems, and lowering the clock speed sometimes just doesn't help, right? And the point is that in this diagram here, this clock can be, once a second, right? The fast clock can be like a 50 megahertz clock, right? So I've got plenty of time. Half a period for me is half a second, maybe, right? Of the original clock. The fast clock can be, 20 nanosecond clock. It gives me plenty of time, and it doesn't even eat into even half a period, right? Taking 40 nanoseconds out of half a second, of a half a second half period would not affect me at all, right? So, but it's still necessary. It's still necessary because, like we see, it doesn't matter what the clock speed is. in cases of skew for these types of errors, right? Yes? Questions? Okay, so to summarize, you need to know what global clocks and local clocks are, when it's appropriate to use each of them, what is the advantage, disadvantage of each of them, and how to overcome skew either by using domino logic when you can, if you run out of global clocks, and if you can't do it, then maybe by artificially generating hold time, especially in cases where the compiler either tells you it cannot meet timing due to skew, or if it can meet, it tells you that it can meet timing due to skew, but it's just wrong, right? And you have to be able to recognize those conditions where it is wrong. Okay, so, and it's not easy sometimes. And in terms of this diagram, everywhere there is a question mark here, that's where your judgment comes into play, right? So you have to build up that experience, but that's with time, right? Okay, questions? All right, so see you next time. All right. Hopefully, if it doesn't snow again.